Thank you very much. It's my pleasure to be here and to present to you today. Thanks very much to Aruband for the invitation. I'm a professor at UCL in computer science, and also I lead a center that's focused on innovation for intervention and surgical sciences. And today I'll speak about some of the work that particularly my research group has been doing in AI for surgical analysis, surgical video predominantly, and video and diagnostic procedures in surgery and interventions. Also, for full disclosures, some of the work that I'll be showing is done in conjunction with digital surgery and also with Odin Vision, a UCL spin-out. So the reason why I think surgical video is particularly exciting is that more and more digital cameras are being used in surgical theaters around the world. So you can see a few examples of the type of image that might be acquired from surgical microscopes that are digital now in cataract surgery or in neurosurgery. And as procedures have shifted towards the minimally invasive or keyhole paradigm, then cameras are increasingly also used in the GI space and also in procedures that normally wouldn't have required a camera, such as in orthopedics. And so this provides an extremely rich signal. It provides us information about what the anatomy looks like, so encodes information about structures and the pathology, but also it embeds information about activity, the position of instruments, the interaction between instruments and tissue, the events that occur during a case. And so it's really the richest signal that's available during a surgical procedure today, and it's freely available in an increasing number of cases because it's the signal that's used by the surgeon, the human, to operate. And currently, I would say that this is one of the least utilized signals from surgery and interventions. And the reason for that is that it's quite difficult to work with this video information and to extract useful high-level meta information from it. Nevertheless, obviously with the boom in AI and in computational power and in availability of cameras and of storage, I think there is now a great opportunity to start utilizing some of this information indeed. So a variety of devices can be used to collect information like this. You can have devices that are flexible, that contain multiple channels, so that you have not just monocular, but stereo or even trinocular information. They may have a variety of visualization angles, diameter to be inserted in different parts of the anatomy. So really a very wide range of devices. Some of these are robotically controlled, robotically held, as you can see in the image on the bottom left. So that's the more successful robotic surgery system, the intuitive system, which has a stereo laparoscope that's used to conduct the procedure. Others might be mounted on beams, for example, surgical microscopes. So they come in a variety of form factors, shapes and sizes, magnification capabilities, resolutions, spectrum of light that they're interrogating, all the way through to devices that potentially could be swallowable and travel autonomously through the gastrointestinal system in order to provide diagnostic tests. And maybe in the future, these may have additional capabilities in order to provide therapeutic capabilities also. So a wide range of devices, all collecting very rich information, huge amounts of data storage required to keep it. And of course, it would be great if we can start utilizing some of this information. So today I'll really discuss the way that we have been approaching using surgical and interventional diagnostic video in order to potentially solve clinical problems. And I'll approach my presentation from the perspective of understanding surgical scenes or understanding what is happening in surgical scenes, and the different dimensions that we may explore this understanding in. So one of those could be the semantic dimension, high-level labels of what's contained within the image. Another could be the spatial, so what is the surgical site geometry information that we can extract from the video, what's the 3D shape, what's the motion. And a third is the temporal domain, and that embeds information about activity, recognition of events, workflows, and the type of actions that occur during a surgical case. So I'll start with the spatial domain because it's one of the earliest that I personally worked on and that my team has invested significant time and effort in. And in the spatial context, we essentially want to extract information about the geometry and the motion of the surgical site. So I'll play this video that provides an example of the type of data that we can extract from a stereo laparoscope. So this is an early video recorded by the lung robotic surgery case on the lung. And here we're using the stereo camera to extract depth, so computational stereo, and also to extract the scene flow, so the 3D motion of all the structures in the surgical site. So this is geometry, metric measurements about the size and the position of instruments and of tissues and how they move during a surgical procedure, extracted optically without any additional hardware sensing. If we link this to measurements that we can take that estimate the pose of the camera within a scene like that, which can also be done using purely the visual information, we can start building a much wider map. So in the video on the right, you see how this information fuses over time in a prostate case, where you can see the prostate in the center of this map of the 3D environment that's being built, and then the pelvic anatomy surrounding it. So in this case, the problem is actually ill-posed because you've got joint motion between the camera and the tissues. And so you need to alleviate for this and somehow only use the rigid constraints within the scene in order to map the motion of the camera. But nevertheless, it seems to work pretty well. And so in addition to extracting temporal 3D depth maps and motion, you can actually build this into a much larger map of the entire surgical site as the camera moves. Now, we initially started working on this spatial domain because we thought that it's an important component of being able to provide image-guided surgery or augmented reality during surgery. So if we have a map of the 3D geometry of the surgical site, if we've got the information about how the camera moves within the surgical site, then potentially we can do fusion. So we can take preoperative information, so models that have been extracted from tomographic imaging, and we can overlay this on top of the surgical video, and we can maintain this alignment as the camera moves or as the geometry deforms. So the cameras in this case are essentially used as the sensor that does the environmental mapping that enables this, this fusion. Much like technology that's now incorporated into the HoloLens or into autonomous vehicles, where you need the environmental mapping in order to do the overlay. This is some really nice work done by Stefan Cotin's team, looking at how the visual field or the visual information could, in addition to doing rigid AR, could be used to also augment the way that organs deform and move. So in this particular case, we're using vision to extract features and their motion in the image space, and then use this as forces onto a finite element mesh in order to deform the organ, in this case a liver, and potentially update where structures of interest for the surgeon may be in that spatial context. So this type of technology is, I would say now, quite mature, although the deformation aspect is still very difficult to get running robustly. But there's a number of exciting studies coming out around using image navigation technology like this in robotic surgery and in laparoscopic surgery, particularly around kidneys, most recently from what I've seen. Now, in the endoscopy space, using the camera to extract 3D information is much, much more challenging. So you see a video of colonoscopy on the left. And here, typically, you only have a monocular camera. And so you don't have stereo measurements. You don't have time instant 3D depth maps. And extracting 3D information and creating a map of the colon, in this case, is actually really, really difficult. One way that we've been approaching this problem is to try to train systems on simulation environments. So this is an example of a virtual fly-through in a simulation environment. So CT scan of a colon, put into a simulation framework. You can generate infinite numbers of training data, of fly-throughs of the camera within this environment. Obviously, the texture is not particularly great. In this case, actually, it's not textured at all, but you get very nice 3D depth information for free. And you can potentially train estimator networks to estimate depth on this data. So we've done some work on how we adapt this to work on real endoscopy video, and it seems to actually to work very, very well. So we can essentially train in simulation, use a GAN-style approach to transfer this onto the real video, and suddenly from a monocular endoscope, we have a something akin to a computational stereo system in this monocular application. The problem is still far from solved. So linking these depth maps in time and creating a map of the entire colon is extremely, extremely difficult. Still very hard to get it to work robustly. And so we're very fortunate to be working on this for the next 4 years within this European Open FET program, EndoMapper, alongside some top European teams in computer vision. So the entire project focused on solving this navigation and mapping problem in endoscopy. Another aspect of the spatial domain that we have investigated developing algorithms for is expanding the field of view. So in certain applications, the scope is so small and the camera field of view is so narrow that really it's very, very difficult to orientate yourself and to understand the entire environment. One particular application we had in mind was in fetoscopy and in twin-twin transfusion syndrome treatment. So here, the field of view of the endoscope is very narrow, and we want to mosaic how the images link together in order to create a map of the placental wall. So some really nice work performed in this space by Sophia Banner, a very bright researcher on the team. And more recently, we've been looking at how to advance this type of mosaicing technology even further and potentially incorporate some semantic information around what vessels look like or what type of structures may be present in the image. So in this latest work, which was actually just recently published at MICI, we are essentially segmenting the image into a vessel map. So you take the fetoscopic image on the left, you predict a vesselness map on the right, and then using this information in order to fuse these vessel maps and to create the vessel mosaic, and potentially using this in order to alleviate some of the problems with standard direct image mosaicing or with feature-based image mosaicing and reduce the amount of drift. So as you can see, the vessel mosaic that we can generate seems to link very, very nicely, and this is an example of how this looks on the rear images. So you can see how the image method drifts and the vessel-based method aligns these vessels very well. So you can see the joinage between different images of the vasculature is very nicely estimated with less drift, despite the fact that there's turbid motion in the image due to the fluid immersed environment and due to potential occlusions. So those were some examples of what we've been doing in the temporal domain. Now I'll speak on a few examples of what we've done in the semantic domain. So the semantic domain essentially refers to taking an endoscopic or laparoscopic image and then labeling different structures within it. Those could be instruments or organs, critical structures or substructures within organs, and so forth. So this is what a semantic algorithm may look like. So this is essentially Deep Lab v3, I think. So it's a classic computer vision semantic segmentation for images. And it's trained on a data set released by Intuitive as part of the Endovis challenge around 3-4 years ago now. And you can take the robotic surgery image on the left and then estimate which part of the image space is occupied by an organ, such as the kidney, which part is occupied by an instrument, whether it's the instrument shaft or the instrument tip. So a number of different semantic labels can be estimated automatically using an AI algorithm. One of the big challenges we have in surgery is that this data set in 2017 was composed of only 400 images. So very, very small number of data points. Whereas in classic computer vision, we're obviously looking at huge data sets with tens of thousands, if not millions of images. And so we still are struggling with this data aspect in surgical and interventional applications. So this year, we released a slightly enhanced data set. This is for cataract surgery. So again, part of the Endovis challenge a few months ago at MICI. And in this case, this semantic data set is 10 times larger than the previous one. So it's got around 5,000 images in order to do semantic segmentation in cataract surgery. So here you can see really, really high quality labels. Every part of the image, every pixel has been labeled. I think around 20 label classes, because each of the instruments, and there's around 14 of them, is a different class. Each of the anatomical structures is a different class. So very, very rich data set, several thousand images, but still, of course, nowhere near the large computer vision data sets. So this is work done in conjunction with digital surgery, who very nicely for them released the data to the community. So in addition to segmenting every aspect of the image, a lot of work has gone into detecting instruments in particular, and also segmenting the shape of the instrument and also the articulation points of the instrument. Now, having semantic information about instruments is quite important because it has implications, or it can be used for inference about what activity is happening at the surgical site. It may be used to control instrumentation, active instrumentation. It may be used to link to the robotic system and potentially provide automation. So a lot of interest has gone in detecting and tracking different types of articulated instruments. And some of these algorithms are quite mature now. But again, there's a problem with the availability of data. So in this particular algorithm, I think we trained on several hundred images, manually labeled, so fully supervised network. But it estimates the articulation joints of the tool and where the tools are. But we need those labels. So we've been trying to move away from needing the labels. And this is a paper we published at MICI this year, where we're essentially combining synthetic labels of the instruments, because we've got CAD models provided, thankfully, from Intuitive. We've got CAD models of what the instruments look like. We can articulate those CAD models and generate simulation images with synthetic masks and ground truth masks. And we can also use the Da Vinci Research Kit. So we have a physical Da Vinci research platform. We can use that to generate real data with kinematic information. And we can use this now synthetic and real data sets in order to try to train networks that perform instrument detection and articulation detection and segmentation, but don't require lots of supervised labels. So in addition to high-level labels and instruments, We may also want to extract semantic information that has pathologically meaningful labels on it. And in particular, in gastroenterology, we may want to detect structures that are abnormal or unhealthy, such as polyps. So the video on the right shows a colonoscopy procedure where an AI system is estimating where polyps that could be precursors to cancer or could be cancerous are. And this is really, really important because in gastroenterology, up to 20% of polyps can be missed. So there clearly could be value on having AI systems that verify that every part of the anatomy has been explored, such as we're looking at in the Endomapper project, and also that detect each piece of textual information that could be somehow relevant for the clinical examination to be as good as it possibly could be. So despite the fact that systems like this have been explored for a very long time, it's only really in recent years that they're reaching the maturity and the robustness necessary to be translated in clinical practice. But I'm very excited to say that they are. And so a number of companies are looking at this, including a spin out that we created at UCL, Odin Vision, that now has a CE regulated, so CE approved clinical device that is commercially available for AI detection of polyps and characterization in colonoscopy. So really exciting to see the development of algorithms go all the way through to actually available systems that can be used in clinical practice. And we're still working on improving this. So we published at MICI this year a paper using kind of both spatial and temporal features in order to enhance the robustness and the smoothness of the predictions and the segmentation of the polyp detections that the AI system is able to achieve. Outside colonoscopy, of course, this type of technology has lots of applications in upper GI as well. So these are some examples from technology that Odin is developing in order to detect Barrett's neoplasia. And this is also something that's going to be a clinically available product in the coming months. So I've talked about the spatial and a little bit about the semantic domain of what we could extract from images. And I'll spend the last moments of my presentation talking about the temporal domain and what we might do with recognizing events or actions that require this space-time information that video has. So for surgical workflow analysis is really important in terms of understanding what occurred during a surgical procedure. And that could be in order to understand what is best practice, in order to understand whether there's a risk, potentially to detect certain events that might be of interest, or to structure better the administration system of managing a surgical theater in order to ensure that it's optimally working. So these are just some examples of AI technology being used to understand surgical workflow and analysis. And this is work that's commercialized by digital surgery. So this is an example on the left, taking a surgical video of cataract microsurgery, estimating the tools that are present in the video, estimating the phase of the procedure that the video is in, and doing all of this for free just because the video is available. So at the end of the procedure, you can essentially end up with a report that says which instruments were used, where were they used, which phases occurred, were they completed successfully, what was the time for each phase. And so you kind of have an intelligence report of what happened during the surgical case. Another example in endonasal surgery, so neurosurgery on the pituitary gland. Again, taking the video, we can detect the phase of the procedure, we can detect the instruments being used in the procedure, and at the moment, we're predominantly focusing on this course level understanding of phases, but of course it could be much finer and look at events, actions, steps, and so forth. So the video can give us some recognition of what is happening during a case. And this recognition can be then delivered back to an end user. For example, it could be delivered back to a surgeon, sort of giving a report of what their procedures or what their typical cases look like, mean procedure time, any deviations, and that could be important, relating that information to particularly challenging anatomies or particular patient demographics. The report could be viewed in a very different way, so you can slice and dice the data in a variety of ways, so that, for example, a hospital administrator may visualize information that's relevant to them to optimize how theaters are used, or potentially a whole clinical unit may standardize particular practice or may analyze how they make clinical decisions. So I think we've reached the point where technology like this is going to be available. These are products that are being sold by digital surgery now. And this is really exciting because it's really kind of leveraging information that has been available, but we've never really been able to utilize before. And potentially now we might find real value from it. Now, of course, the labels that we denote as phases or actions can be fairly arbitrary. So this is one example of some nice work done on vitoscopy in our group, published at IPCAI this year, where the event labels are essentially identifying whether there's an occlusion in the video. And occlusion in this case means that a fetus is observed and therefore instrument use should be limited. Or whether the view is clear, or whether potentially there's an activity happening such as ablation. And this is really important because, so for example, in this type of procedure, you use a laser to photocoagulate vessels. Well, if you can automatically detect occlusion, so the fetus being in view, then potentially you can have active instrumentation that is intelligent. So you could prevent the laser from firing in order to mitigate risk. So it's just one example of how workflow analysis and activity recognition could go beyond recognizing just reports or delivering reports, but it could link to active instrumentation and the type of capability that instrumentation may give. So you can see here the AI system predicts the labels fairly well in terms of what is observed in this image that is actually quite poor quality. And so, it's really exciting to see that networks can do well in this data. I should say that these data sets are still very, very limited, and we're very excited to be trying to increase the size of these data sets and potentially to stimulate growth in this area with more challenges. Now, if we look at very fine-grained activity recognition and analysis, so rather than just understanding phases, which could be quite a coarse representation just below the recognizing a type of procedure, activity could be broken down into quite fine-grained tasks, such as dexemes and sergenes. So if we look at the workflow of a particular activity, such as suturing, it may be composed as a workflow diagram of a number of decision points that an AI algorithm can detect. And these are then very, very fine-grained understanding and analysis points that you could extract from the video and potentially from the kinematic signal. Now, this is potentially extremely helpful for surgical training and education. So if you can do such fine-grained analysis, then potentially you could have systems that are able to steer or to provide feedback to trainees as they're developing their competence training program. So in this particular case, the Jigsaw's datasets from Johns Hopkins, you have a silicon phantom and lots of tasks of suturing, and potentially we can do automated analysis of activity like this just using the video and maybe the kinematic information. So in this paper, we published this at ICRA earlier this year. We're essentially taking the kinematic signal and segmenting this very fine-grained gestures that are being conducted during these phantom-based suturing experiments. And in this particular case, the novelty of the paper was really about linking how this progress links over time, rather than doing it very kind of spatially. So in essence, we can build systems that can achieve this sort of fine-grained level of recognition. But again, the number of data sets, the robustness of these systems needs more work in order for it to be understood in greater detail. So I'm running out of time, and I've spoken about 3 particular directions that we might interrogate in this exciting domain of video, surgical video understanding. But of course, there are other directions that are also very, very interesting. For example, the spectral domain. So if we change the illumination wavelengths, the sensitivity of the sensor, we could extract very, very interesting information. And we are also working in that direction. There's also the whole room domain. So, you know, there's a lot of interesting information that's contained within the room itself about how the team interacts, what decisions are taken, that is not observable in the camera that's inside the patient. And so some teams around the world are doing some really exciting work in that space. So I think it's a very exciting area to be in, potentially linking this room activity with the activity inside the patient. I'm very glad to have had the opportunity to present some of our efforts in this space to you, and I look forward to our discussion and any questions that you may have. Thank you.